In this lesson, we're going to talk about the concepts of stoichiometry and percent yield. First, that word stoichiometry, it's long and hard to pronounce and spell. It refers to the calculation of quantities of reactants and products in a chemical equation. In other words, we're finally going to put numbers to the stuff that we've been talking about qualitatively throughout the year. In stoichiometry, we're unpacking lots of information that is embedded in chemical equations. And as you'll see, it's extremely useful for chemists. Let's do a little warm-up. I'm going to give you a balanced equation. I'm going to ask you what kinds of molar relationships are revealed. Well, look at these coefficients in front of H2 and CO and CH3OH. Notice the coefficients are 2, 1, and 1. Those coefficients are going to tell you a lot. For every 2 moles of H2 that reacts, 1 mole of CO reacts along with it. For every 2 moles of H2 that reacts, 1 mole of CH3OH is produced. For every 1 mole of CO that reacts, 1 mole of CH3OH is produced. We related each molar relationship to another one within that chemical equation. These molar relationships are what enable us to convert from moles of one substance to moles of another. So the coefficients in a balanced chemical equation are of utmost importance in stoichiometry. The other thing that's going to be of utmost importance is the technique called dimensional analysis. What if I asked you how many seconds are in a year? You might say, oh, okay, well, here's what I'm going to do. I'm going to start multiplying. I know that there's 60 seconds in a minute. I know that there's 60 minutes in an hour. I know that there's 24 hours in a day. And well, I know that there's 365 days in a year, at least a year that's not a leap year. And I just multiply all those numbers together. And yes, you would get the right answer. But I want you to pay attention to the units as well. If I say that we have 1 year of time, and I want you to convert that 1 year of time into units of seconds, you can write a series of conversion factors. You see the big sets of parentheses? Notice that in each of these big sets of parentheses, the numerator is equivalent to the denominator, but it's stated in different units. 365 days is equivalent to 1 year. 24 hours is equivalent to 1 day. 60 minutes is equivalent to an hour, and 60 seconds is equivalent to 1 minute. But the way we've laid out these sets of parentheses, and specifically the units on top and on bottom within the sets of parentheses, is extremely important. Notice how the unit year crosses out. You see the black slash marks? If you start with a year, and in the first set of parentheses, year goes in the denominator, then that unit year goes away. Days, look at the red slash marks. If the unit day appears in the numerator in the first set of parentheses and in the denominator in the second set of parentheses, that unit goes away. Hours, in the numerator of the second set of parentheses, but in the denominator of the third set of parentheses, means that it can go away. Minutes, in the numerator of the third set of parentheses, but in the denominator of the fourth set of parentheses, means that that unit minute goes away. The only unit that did not cross out is found in the numerator of the fourth set of parentheses, seconds. And that's exactly what the answer asks for. It says how many seconds are in a year. So we want to set up in a stoichiometry problem a series of units such that most units will cross out, and the only one that does not cross out is the unit that the question asks for. As we do this, we're going to pay close attention to the units. Notice that each unit is crossed out until you reach the unit that the answer should be in. We sometimes call this The factor label method, or dimensional analysis, I think is what the math teachers say. And we're going to use this technique as we work stoichiometry problems. Let's start with an easy one. Here's that same balanced equation from before. If 2.35 moles of H2 react, how many moles of CH3OH are produced? We know from the balanced coefficients in the equation that for every 2 moles of H2 react, 1 mole of CH3OH is produced. So what we're going to do is end up dividing 2.35 moles of H2 times, in parentheses, 1 mole of CH3OH for every 2 moles of H2. That'll enable us to go from the unit we begin with to the unit the question wants. And after making that division and rounding to 3 significant figures, we would get 1.18. How about this one? If 5.46 moles of CH3OH are produced, how many moles of H2 reacted? Again, it's a 1-to-2 ratio between the substances we're interested in and that they give us information about. For every 1 mole of CH3OH, 2 moles of H2 reacted. So this time we'll write 5.46 times 2 moles of CH3OH over 2 moles of H2 over 1 mole of CH3OH that was produced. In effect, we're multiplying by 2. And if we round to 3 significant figures, you would get 10.9 moles of H2. Ooh, okay. Is there a way to put this together? Well, take a close look at this. If we're going from moles of one substance, let's call it substance A, to moles of another, we use the mole ratio from the balanced equation. In other words, pay attention to the coefficients. But then we know from before that you could get from moles of one substance to its mass using its own molar mass. So you can get from moles of substance A to mass of A using the molar mass of A. You can get from moles of substance B to the mass of substance B using the molar mass of substance B. If we keep that all together, let's try a couple of tougher problems. And to do this, I'm going to navigate over to another app here called Jamboard. Here's our problem. Same balanced equation as before. If 14.5 grams of CO react, how many moles of CH3OH are expected to be produced? In particular, we're going to want to pay attention to where we begin with in the problem. We're starting with the mass of one substance, let's call the CO substance A. And they want us to get to not mass, but moles of another substance. So we're getting to moles of a substance B, let's call substance B CH3OH. On this stoichiometry roadmap, we're going to make 2 hops. The first hop is going to involve the molar mass of CO, and the second hop will involve the molar ratio from the balanced equation. We need to actually get the molar mass of CO in order to solve this problem. So that means break out your periodic table. And let's do a little bit of work here. Within the formula CO, there's only 1 carbon atom. And carbon's atomic weight, if you round it to the 10th place, is 12.0. So if I take 1 times 12.0, I'd get 12.0. Oxygen's atomic weight, if you look it up and round it to the 10th place, you'd get 16.0. So 1 times 16 gives me 16. Then we're going to add together those 2 numbers and get 28 grams per mole for the atomic mass of CO. Okay, so 28 grams per mole. That information is going to go into the first conversion factor. And specifically, we're going to write it so that 1 mole of CO is equivalent to 28 grams of CO. We want to make sure that the first unit, the unit we begin with, crosses out. So if the first unit is grams of CO, that means I want the unit grams of CO to go in the denominator. So let's make sure to write the 28.0 grams of CO down low, and we'll write the 1 mole of CO up high. That ensures that as you do the calculating, the unit gram CO crosses out. What was the next hop in our conversion factor here? Well, we're going to use the mole ratio. Well, we're trying to find out how many moles of CH3OH are going to be produced by a certain amount of CO. So that means we're going to pay attention to the coefficient 1 in front of the CO and 1 in front of the CH3OH. From those balanced coefficients, I can see that one mole of CO is equivalent to 1 mole of CH3OH. And you might say, gosh, then do I really need to write that conversion factor since it's a 1-to-1 ratio? The answer is yes. I want you to write it out because I want you to show me the unit crossing out. So I want to see in the denominator 1 mole of CO, and I want to see in the numerator 1 mole of CH3OH. And I want to see how the unit mole of CO crosses out because it's in the numerator of the first set of parentheses and the denominator of the second set of parentheses. Now for the fun part, I want you to multiply 14.5 times 1 times 1, and then I want you to multiply 28 times 1, and I want you to divide 14.5 by 28, and that should give us our answer in the unit we need, moles of CH3OH, and we get 0.518 moles of CH3OH. So there's quite a bit of work in a stoichiometry problem, and this one involved 2 steps. We can get even tougher ones, like this one. This time, they tell us a certain number of grams of CO. If 47.0 grams of CO reacts, how many grams of CH3OH are expected to be produced? So this time, we're going to go all the way from the very left edge of our stoichiometry roadmap to the very right edge. The first conversion factor, what's going to go in the first set of parentheses, is the molar mass of substance A, the CO, which we figured out earlier, so we're not going to redo that. In the second conversion factor, the mole ratio, which was 1-to-1, if you remember. And in the third conversion factor, we're going to put the molar mass of substance B, which we do need to figure out. Let's first write the info that we had. So referring back to the previous problem, it was 28 grams for every 1 mole of CO. And then the mole ratio was 1 mole of CH3OH for every 1 mole of CO. Let's rewrite that in the first 2 parentheses here. And then we're going to notice what units can cross out, which is of utmost importance here, making sure that these units cross out so that we end up with the unit that the question asks for, which is grams of CH3OH. The last conversion factor we're starting to fill in here, but we don't have the number yet. We don't know what number of grams is equal to 1 mole for CH3OH. We're going to figure that out next. So if we take a look at what units cross out, we've got grams of CO, moles of CO crossing out, and we're going to set this up so that moles of CH3OH crosses out. The only unit that does not cross out is the unit they want in the answer. Since the question specifically says how many grams of CH3OH are expected to be produced, we want to make sure that our unit in the answer is going to give it what it asks for. Okay, so we've got in the first conversion factor, the molar mass of CO. In the second conversion factor, the mole ratio from the balanced equation. And the third conversion factor, we're missing a piece of information. We've got to get the number of grams of CH3OH to get the molar mass. So let's look up on our periodic table. We're going to do a little calculating. There's C and H and O in that formula. There's one atom of carbon, and carbon's atomic weight is 12.0. If you look up carbon on the periodic table, you would see 12. For hydrogen, hydrogen appears both after the C and after the O, so you got to add those together. Altogether, there's 4 atoms of hydrogen, and its atomic weight is 1. So times that by 4, and you get 4. For the oxygen, there's only 1 atom, and its atomic weight is 16. So if we add that all up, we arrive at 32 grams per mole. So for every 32 grams of CH3OH, we would have 1 mole of it. Sometimes it's even helpful to write that out. I think 1 mole of CH3OH is equal to 32 grams. So if we look at that third conversion factor, the missing piece of information, the number that we need, is 32.0. Now for the math part, and which I think is the fun part, we're going to take on our calculator 47 times 1 times 1 times 32. Write that number down. So multiply all of the numerators together. We get 1504. And then we're going to multiply 28 times 1 times 1. Write that number down. Take the top result by the bottom result, and we get 53.7 grams of CH3OH. That's our final answer. Woofta, there's a lot to this, isn't it? Especially with a mass to mass conversion. If you're going from grams of one thing to grams of another, that's going to involve 3 conversion factors. There's one last thing that we need to visit along these lines, and that is the concept of percent yield. Whenever you do a stoichiometric calculation, you're finding what's called the theoretical yield. It's the amount of a reaction, amount of product typically of a reaction that is predicted by stoichiometry. We never actually get that. I mean, in the most perfect laboratory, you might get something approaching 100% yield, but you're never actually going to achieve that. Instead, we get something that is a percentage. Like students in my many years of teaching, I've never had anybody get a 100% and never miss any of the questions that I posed in a year of chemistry courses. Somebody's going to get something wrong. It's just normal. But we can quantify the difference between what we think you should have gotten and what was actually gotten. It's a simple calculation. You take the actual yield, what you actually got in lab, divide it by what you would have gotten by stoichiometric calculations. That's called the theoretical yield, and then times it by 100%. Let's walk through one sample problem. If stoichiometric calculation predicts that 688 grams of CH3OH should be produced, but in actuality, only 357 grams is produced, calculate percent yield. So they say our theoretical yield, what stoichiometric calculation produces, 688. What we actually got was something less than that, 357. Take 357 over 688, times it by 100%, round it to the nearest percentage when you do so, and you got your percent yield. If your percent yield is ever over 100%, that's a sign that you did the calculation wrong. Maybe double check your work. And I would lastly point out, this is the same calculation we do every day in a class. The percent you get on a test or a quiz is like a percent yield. Theoretically, you should get all the questions right, but students, we all know that that doesn't happen. So you get some percentage correct divided by the number of questions possible, and that gives you your percent. It's much the same way in chemistry. Good luck on your homework.